Hello everyone and welcome. We are finally going to go through the last of the SMO rounds this year, which is the Open Round 2. This is delayed by a couple of days as I have mentioned because on the day itself, my lessons have already started, and so this is basically the next time when I've been able to get access to a proper recording environment. And also, of course, admittedly, the SMO Open, no matter how, is going to take a bit longer to work through than, let's say, the SMO Junior. So it is natural that a bit more time is needed, both to solve the questions and also to just package it in a way that is reasonably understandable. Now, since this is a couple of days after the SMO Open has already taken place, many of you who took it, whether as an Open Round 2 or as a SIMO selection, have kind of already discussed how you did, right? And I hope you did well, and I hope you're happy with how you did. I think it's pretty much consensus. There isn't really a lot of dispute about this, that the last two questions are harder and the first and third question are relatively easy. So by the standards of Open Round 2, question 1 as well as question 3 are quite straightforward. Of course, we will go through everything in order, but we acknowledge that 1 and 3 are relatively straightforward. 4 and 5 are a bit more challenging. We will also go through them, but as I'll share, 4 and 5 are proposed by a couple of our ex-IMO team members. Now, question 2 is kind of in between, and this is probably going to be the deciding factor for quite a lot of things, whether it be for getting to the top 30, whether it be getting to the national team. How you do on question 2 is going to be quite significant. And when I say how you do on question 2, I can't tell you right now, but you probably know yourself whether your proof is valid to some extent. Now, we'll go through in order anyway, but my comments are that there is a clear difference between the difficulty of 1 and 3 and 4 and 5. So a lot of you who have gotten somewhere between 2 and 3 questions, just be happy you have done reasonably well. But what exactly does that translate to? I find it a bit harder to say. Let's start with the geometry question. For the Open Round 2 in recent years, the geometry question has almost always been at question 1, and it's almost always been so-called one of the questions that you would hope to be able to do. But this question is really quite friendly because there are no circles, which is always nice. And we've got a 90-degree angle and equal lengths. That's also nice. So let's just start drawing this and see what happens. This is the triangle ABC, where AB is greater than BC. Now P is the point such that BP equals to BC and APB is equal to 90 degrees. Now in some sense, you can just draw a semicircle like this just to get a rough location of P. P would be somewhere here. You don't really need the semicircle. You could also keep it there. Some of you may have drawn a lot of circles which are reasonable because of the 90 degrees and equal lengths. But let's just not do that to avoid any unnecessary complications. These two are equal in length and we have a 90 degrees. Q is the point on AB such that AP equals to AQ. So I've drawn it like this because there's also now here's the equal length. This is Q, and M is the midpoint of QC. Prove that the line through M parallel to AP passes through the midpoint of AB. So you want to draw in an extra line which is parallel to AP, I think it is easier to just name the midpoint. So I'm going to name the midpoint D. Of AB. I'll name the midpoint D, and instead I want to show that MD is parallel to AP. Obviously this is the same task. Now in turn, if I want to show that these are parallel, I've got a few potential strategies I could use, right? Because you could show some equal angles, you could show some similar triangles, you could show, well, quite a lot of things. There are certainly some of you who solve this using coordinate geometry. And I support that. I support that this is a very suitable question for coordinate geometry. However, when I sort of did a little bit of like a thought experiment about how I would do the coordinate geometry, I realized that, in order to show via coordinate geometry that MD is parallel to AP, I would show that they have the same gradient. Now to show that they have the same gradient, I would essentially be showing that the horizontal over vertical displacements are in the same ratio for both. And then I realized that I could actually kind of do that without having to use quad geom at all. So let me adjust this a bit because I know what's going to happen in a second. So I think my midpoint was not very well drawn. Okay. So what I want to do is essentially to get the gradient of this stuff. And then I realized that because of all the midpoints, actually, if you tried to get this point here, which is, to obtain the gradient of DM, so to speak, it actually lies on AC. One way to put this simply is that if I were to call this point here N, then by your midpoint theorem, you're going to get ND is parallel to BC, and also NM is parallel to AQ. In other words, if I'm considering BC as horizontal and BA as vertical, this is pretty much what I want. So the good thing is that this would kind of be my gradient. And meanwhile, if I were to try to draw one for the horizontal of AP, call this point here, let's say PQR, let's call it R. Now this triangle ARP is going to be similar to APB because it's just nested right angled triangles. So this is great because if I let R be the projection of P onto AB, then what I need, essentially quad geom, is that AR over PR is equal to NM over ND. And I put it to you that this is not very hard to do. Now at this point we have not used any of the equal lengths yet, so that's why I suspect that this is not hard to do, because you like to have as much information in reserve as possible. I've only used a midpoint so far. So AR over PR, I can move this to AP over PB. By similar triangles. And AP over PB, I just know that I want to shift it over to AQ and BC. That's the stuff that I know from the question. But then I'm kind of immediately done, because AQ, by the same midpoint theorem, is just 2 times of mn, and bc is 2 times of dn. So these are equal, and that is basically going to be my equality chain. Right? This equals to this, equals to this, equals to this, and that gives me what I want. To be honest, I don't mind this so much as an approachable question in the SMO Open Round 2. It may be a bit disappointing for those of you who are strong at geometry, because this did not really require you to know a lot of geometry at all. But I don't mind this as 1 of 5 problems in a 4-hour contest. I'm going to jump ahead next to question 3, because that's the other one that I felt is relatively simple. It's relatively simple because of more or less how you probably go about doing this with small cases. Also tells you how you should do it in general. Right? Small cases would be that, okay, A1, 1-digit number which is a multiple of 5 is 5. Now I want 2-digit number which is a multiple of 25 and the digits are odd. So that's 25, 50, 75. Now I want a 3-digit number that is a multiple of 125. So it's an odd multiple of 125. The next one, 375, that already works. Now I will also note the fact that it's supposed to be unique. Right? So among the odd multiples, all of them have some other even digit somewhere. But that's not very surprising, because essentially, if you wanted to continue, now you want a multiple of 625, it doesn't take too long to see what's going on. So odd multiples of 625 is what I am calculating now. And so far, lots of even digits appearing. And here it is. At which point it is fairly obvious what is going on just by looking at the small cases. They are simply building up. They are formed by adding one more digit each time, and so if you are just adding digits each time, this is clearly going to be an inductive solution. Now your induction hypothesis is kind of literally stated here, that there is a unique n digit, so suppose true for n, and now I want to go to n plus 1. So I want an n plus 1 digit number that is all odd digits and divisible by 5 to the n plus 1. Now I said that we have to extend from the previous case using our observation of the small examples. This is both we can and we must. Right? We can extend and we must extend because I want to show it exists, there is, as well as unique. So existence and uniqueness are both in the induction hypothesis. Right? So my an plus 1, if I want to use the induction hypothesis, I'm going to sort of go both ways. Right? It will actually be just the last n digits if we consider it mod 5 to the n. Because once you reach the n plus first digit, its place value is 10 to the power of n. And this is supposed to be 0. Since it's divisible by 5 to the n plus 1, it's also divisible by 5 to the n. That would immediately imply two things. First implication is that the last n digits can, and the second is can only be the an from the induction hypothesis. So it can and it must be following that. And then now I need to put one more digit in front. Now, if I put one more odd digit in front, it will be one of these. So 1, 3, 5, 7, or 9. And all I need to do is to make sure that one of them is going to work. It must be exactly 1. But that's not hard to do, because if I need exactly 1, I can just factor out 5 to the n to make it clearer. I'm going to just let an be 5 to the n times bn. So not 1 plus 1 times 2 to the n plus bn, then 3 times 2 to the n plus bn. And what is the purpose of this? I want to know that one of these numbers has an extra 5 located inside. But it's pretty clear that these are going to be distinct mod 5. They're distinct mod 5 because the differences are just going to be some even number, 2, 4, 6, or 8 times the power of 2. So if the differences are not 0 mod 5, they are all distinct mod 5, and so exactly one of them is a multiple of 5. And if exactly one of them is a multiple of 5, that gives us what we want. So we can find exactly 1. Now, this question is actually not original. This question is taken from the fairly well-known PEN, Problems in Elementary Number Theory. You can find it online. This was 041. I did a quick check just now. You will also find that the recent years number theories have very often been taken from the PEN, right? That includes the Vieta jumping questions of senior 2022 and 23, all from PEN. So I do not personally agree with the choice of taking questions from such a well-known source. But PN has about 1,000 questions, so in this case, if somebody really did all the 1,000 questions, they do deserve to have seen it before. What I agree with a bit less, however, is the question 2, because it's not original. Now, I'm just going to copy in the question that some of you have seen before. And if you have seen it before, you know where it's from. This is actually from Senior 2010. Q3. Now, incidentally, I couldn't really forget this because I just taught this in my round 2 class during the June holidays. So when I looked at it, okay, to be fair, I didn't look at it immediately. The first thing I did was that question 3 looked too induction ready that I did question 3 first. Question 1, no circles, I drew it first. So that's what happened. And then when I look at question 2 a bit more carefully, I say, hang on, I think I've seen that before. And so this is what it was. And yeah, this would clearly be the same situation. In fact, it is more general than the same situation because the equality case of this is when they are all equal to 1 to n, which is also going to be the equality case of this. Yeah, this I have a bit more annoyance about than taking from the PEN with 1,000 questions. A bit more annoyance because, as we've seen, Senior is taking questions from the Open 2010, and now Open has taken a question from the Senior 2010. Well, not ideal, but let's go through it anyway because it's a good question. I don't disagree with the fact that it is a good exercise, very suitable as a question for selecting someone for, let's say, the national team, right? Because the ideas are very commonly used, just not easy but commonly used. Now I'm going to start by saying that I don't think the equality case needs a lot of motivation either. The fact that you should let them be 1 to n makes a lot of sense since they must be distinct. What else do we think they're going to be? Because when cubes are big, they're going to be much bigger than, well, just the value themselves. So logically, this makes sense. And the value it gives you by our cube identity is just going to be the sum from 1 to n. So this is the claimed minimum value. And because I do find it very difficult to not think of this question from Senior, I'm going to just explain it using this. However, I will acknowledge that a smoothing argument, which is that if we assume without log that the, see now I'm calling it A, x1 to xn are in increasing order, then you would be able to essentially say that for each of them, xk plus 1 should be equal to xk plus 1 in order for it to be optimal. This is the kind of argument you will make. Now, how you would make it, some of you did it just by normal bounding, and some of you did it via calculus. Calculus can work, but whether it is correct depends on how you wrote it and whether your justification is sound. So I'm not really able to comment on that right now. Okay, so I'm going to now jump right into the proof of this Senior question, which is by induction. Now, it also does make sense to use induction on the original case because in some sense you are showing that the front cubes can only be this much, well, will at least be this many times of the front sum, and so putting in one more term inside gives a similar kind of intuition. But in this case here, this is more or less showing the same thing. It is showing that the optimum is when you have 1 to n, assuming that everything is distinct, and increasing by at least 1 each time is true of distinct positive integers. Okay, so of course the base case is trivial. And so if we show the induction step, what does that mean? I have got this to begin with. This is by assumption. And then what I want is one more cube and one more thing being squared. Now this would be true if the increase, means the next cube, is more than the difference of squares. And the difference of squares is always nice. We always like difference of squares. This is the difference, and then this is the sum. So this is what I want. I can of course cancel off one copy of the an plus 1. Oops, not equal, greater than or equal to. Now when you do an induction like this, you are not always sure that you are correct. What I mean by this is that it is entirely possible that the induction hypothesis is true but not strong enough to show the next step, and you actually need to do something else more clever. But assuming that this is the approach we are taking, then the right hand side is going to be maximized if I push the a1 to an as close as possible to an plus 1. And the closest you can get to that is just minus 1. So it will be an plus 1 minus 1, an plus 1 minus 2, until an plus 1 minus n. The closest you could go is if they are all just 1 less. Now you realize that of course this may turn out to fail, but we should check. And the number of things that you have is 2n plus 1 an plus 1 minus n plus 1. Right. And so the question is it less than or equal to an plus 1 squared? For which the answer is yes, because if you move this over, it is a very clear factorization. Right. So it's okay, since I know that my an plus 1 is greater than or equals to n plus 1. Okay, so based on what I've written down here, you will see of course that a smoothing argument or just some other bounding argument will tend to have this same kind of character. Not exactly this, but your character is kind of that. The worst case scenario is that all of the x1s to xn minus 1s are packed as closely as possible to xn by an argument something like this. And then you would be able to further show that all of them should be pushed to 1 in the worst case scenario, and it still turns out to be greater than or equals to this value. In fact, equality holds when you push it all the way to 1, that it is the sum from 1 to n, or n plus 1 over 2. Okay, so these are the 3 main questions that will be relevant to a majority of those of you who are taking the Open Round 2 this year. And perhaps for those who are hoping for something like the top 20, those of you who are already in the national team, the 4 and 5 would certainly matter. Now, my understanding, of course, is that there are a few of you who managed to, at least you think you did both 4 and 5, and then there are some of you that just did question 4, there are a couple of you that think you just did question 5. My opinion is that question 4 looks difficult, but it's not actually that difficult, whereas question 5, after you try it and perhaps find a solution, you might think it's easy, but I think it is, at least part of it is quite challenging. Now that's my take on it, but let's look at them both right now. So question 4, Alice and Bob play a game. Bob picks a set comprising m vectors of length n. Please do not panic about vectors. I will use vector notation in my solution just to save some time, but this doesn't use anything about vectors. Vectors are just a length n sequence in this case, right? So just a bunch of zeros and ones. Alice then picks a sequence of numbers from the interval 0, 1 and a choice of real numbers x1 to xn. Bob wins if he can pick a vector in S such that this sum is less than this sum, otherwise Alice wins. So determine the minimum value of M such that Bob can guarantee a win. Now the first thing that came to mind when I'm reading this question is, does Alice know what Bob picked? And the answer is, it does not matter. It does not matter because Bob can guarantee a win means that no matter what Alice picks, he must be able to win. So it's as good as even if I tell Alice what I picked, Alice still has no way to prevent Bob from winning, then Bob can guarantee a win. So you can just assume that Alice knows the set S, in some sense. So my thinking is that I'm going to just pick some small cases first to get an idea of the answer, and I'm going to sort of imagine that Alice actually can see the set. That's my idea. Okay, so n equals to 1, it is not very interesting. It is very obvious it will be 2. So let's talk about n equals to 2, where the options are 0, 0, 0, 1, 1, 0, or 1, 1. Right? These are the options that Bob has. Now, I'm going to just use vector notation, to be honest. Right? I'm going to just let this vector x be x1 to xn, the vector y be y1 to yn, because these are just dot products. Now, if you're wondering what's a dot product, this is the definition of the dot product. Now, if you're wondering what do I need to know of the dot product, for this question, honestly, nothing at all. Except that the dot product behaves like multiplication in many ways. So, like, for example, I could say that this is true if and only if 0 is less than or equals to x dot z minus y, right? Like, which is pretty clear what z minus y would mean. So I'll use dot products to shorten my solution, but we're not really using any vector theory, so to speak. Now, when n equals to 1, you have 2. For n equals to 2, Alice will know what Bob has. So I'm going to kind of think of it as, I want to now treat it as if Alice will be able to take advantage of missing vectors in the set S. For example, Alice, if let's say 0, 0 is not there. Now, the vector 0 would allow Bob to achieve 0. Now 0 doesn't sound like a very good result from this x dot z. Think of it as this is Bob's score. It's not very impressive. But I can make it such that everything else would be negative. Well, Alice can make it by letting x be all negative. Just say minus 100 minus 100. Now, if Alice does this, then she can also, you can see that the scores for Bob will be 0, minus 100, minus 100, minus 200. So Alice herself just picks this one as y. Now, if Alice picks this, then clearly Bob needs 0, 0, otherwise he will surely lose. And this gives me my motivation for something that Alice can do. Alice can try her best to sort of pick different x's that will give different scores for each of these. And maybe I don't really need to put 100, that's just quite exaggerated. Alice can pick different vectors to give different scores, and the different scores will correspond to what Bob could score, and Alice could also get that same score of the maximum. Right, so when it's minus 1, as we have said, is 0, minus 1, minus 1, minus 2. 0 is the winner here, so Bob needs to pick 0, 0. Now, by the same logic, if Alice picks 1, 1, then she can also have y be 1, 1. Remember that y must be increasing, non-decreasing. So 1, 1 is okay, and so it means that Bob is also obligated to have 1, 1 in his set, otherwise he's going to lose. Now my thinking is then going to be that, can Alice also force a 0, 1? She could choose y to be 0, 1. That is allowed. Is there a way to make 0, 1 better than any other choice? And the answer is yes. Alice could make the 1 at the bottom very valuable, and the 0 also useful in this way. Now this would give 0, 1, minus 1, 0, and so this time, this is optimal. But obviously, Alice will not be able to pick 1, 0 as her choice of y because of this constraint. Which means that Alice does not want 1, 0 to be the best for her choice because she can't make that happen herself. So, but Bob is already forced, based on this argument, for n equals to 2, he must include these 3 to have any chance of winning. And now the question is just, could Alice pick something such that these 3 choices are not good enough for Bob? Now if we try to play as Alice, you will find that it is surprisingly difficult, because if let's say you just let x be AB, it means that the scores are 0, B, A, and A plus B. Right? And of course, based on this, Bob is currently able to get any of these scores that you want. Now, Alice, in her choice of y, the score that she will get is AY1 plus BY2, where Y1 is less than Y2, less than or equal to, and they're both between 0 and 1. Now you kind of get the sense that Alice can't really find a way for this to be bigger than all of these at the same time. Right? Because if y1 and y2 are both positive, it's not going to be possible. Okay, not if y1. If a and b are positive, y1 and y2 are positive. If a, b are positive, then definitely having more of a and b are good. If you have something like a is positive and b is negative, it's still going to kind of be true that you are limited in how much of A you can get, because y1 is less than or equal to y2. But I don't really want to go through all these cases so much. So I want to sort of write it more generally in terms of A and B. There will be positives, negatives everywhere, and this is only for 2. So how I would want to write it is that I use this condition to say that I can actually write it as some A plus B's, y1, and then some more B. Now all of these are still upper bounded by the fact that you have, okay, let me write this properly. They are all upper bounded by having a lot of A plus B. Assuming that A is positive. This is y2A plus B. So in some sense, of course, this is assuming that A is positive. But if A is negative, I could have just thrown away A altogether. And this is also going to work. Assuming, of course, that your B is also positive, otherwise it would disappear. Right? So if A and B are both negative, then 0 wins. Right? Kind of like the -1 case just now. This is very sketchy, right, by design, but it gives me the sense that n equals to 2 can work. This will be how the general argument goes. We have already seen how Alice can force Bob to have all of these factors. So in terms of n, your answer is m equals to n plus 1. And basically Bob needs to have all of these all the way until just a bunch of ones. Anything in increasing order must be included in Bob's set, and conversely, anything that Alice can pick can be written into this form. So these are what you can do, and my claim is that because of this, you will be able to ensure that the value of x dot y, which is Alice's score, cannot exceed the x dot z for all choices of z. Now this is the point where I kind of acknowledge that it's not a lot of fun for me to write down the details here. I will be in the description below, including a copy of the more carefully written up solutions which I have. I think for harder questions, it's always enough to just talk about the motivation as well as the rough logic. So I'll leave you to read the details in the solution below. And the same thing will also apply for problem number 5, which we're going to talk about together right now. Let P be a prime number. Determine the largest possible n such that the following holds. Now, this is a big mouthful. Let's just kind of acknowledge that it is like determinants. For those of you who know it's determinants, for those of you who don't know much about determinants, essentially you just pick 2 rows and 2 columns. You pick 2 rows and 2 columns, and when you pick them, the 4 entries you're going to get are these 4. You want to make sure that when you take out these 4, their determinant, or just their this minus that, is not 0 mod p. Let's start with p equals to 2. Obviously, I am able to, let's say with a 2 by 2, satisfy the condition. I want to see whether I'm able to satisfy the condition for a 3 by 3. Let's see if we can extend it. Just to kind of try. Right? So now the logic will kind of be like this. You can solve it like a mini puzzle for p equals to 2, because this times this minus this times this cannot be even. This is already 0, so if this is 0, I fail. So this thing has to be 1. Now same with if I pick these 4, 1 times something and 1 times 0. So this has also to be 1, and by symmetry these have also to be 1. For the one right at the bottom, I don't want it to be 1, because if I do that, then these 2 and these 2, I don't want it to match like that. So I put a 0. And that actually works. Interestingly enough, you can check all the 4 combinations, well, actually not really the 4 combinations, all the 3 choose 2 squared combinations, which is 9 combinations of rows and columns, and everything is fine. So 3 does work. I do hit a bit of a snag if I try to extend this to a 4. If I try to extend this to a 4, there are lots of places that I cannot put a 0 just like just now, but if I have to put all this as 1s, then you have tons of places where it fails. So for p equals to 2, it is quite clear that n equals to 3 is optimal. That doesn't really tell me a lot, but it's a good start. Let's try with p equals to 3. Now, in my mind, I kind of believe that surely I should be able to at least continue on, because if I just did this, I mean, this is still not going to give me anything, right? So 3 is at least going to be possible for 3, if I just copied the thing just now. Now, in general, I'm not so sure if I want to just copy, but here it's fine. I can copy this. It is still okay. And then now let me try to extend another row. Now, if I'm working with mod 3, it means my choices are 0, 1 or 2 essentially, and I don't really need anything else. By the same logic as just now, all of this stuff here cannot really be 0 anymore. And in fact, this kind of just is worth noting, right? That you cannot have 2 zeros in the same row or column. Because if you have got 2 zeros in the same row, then what happens is that you would be able to make a 0 appear. So you cannot have two zeros. I'm saying 0 mod p, but you can take it literally as 0 also without log. You can't have two zeros in the same row or column. That means that I could potentially put a 0 here, but for everything else, I need to decide on 1 or 2. I am not so sure what to do, so let's just try, right? Now I see that these two cannot be the same because of that. I also see that these two cannot be the same because of that. And I also see that these two cannot be the same because of that. So I can't extend this. Right? By pigeonhole, I cannot make those three all different and yet not all 0. This doesn't mean that the 4x4 fails. It just means that I should not actually just blindly do this. And in fact, I kind of see the thing that is going on is that, I can't have the repeats happen in parallel, right? So for example, if these two are the same and these two are the same, then I'm in trouble. I also can't really have, let's say, the repeats be like this, right? Which is now the exact same pair cannot appear in the same corresponding positions. But then I realized that, in fact, it's also true that if let's say that I had this also doesn't work. 2 times 2 and 1 times 1 does not work. And so my choice is basically that once I have 1, 1 or 2, 2, these two kind of block each other, and 1, 2 and 2, 1 kind of block each other. I can only have either one. So let's try to make that happen. Some repeats are therefore forced. I'm okay with repeats, I just don't want too many. So if let's say this is 1, 1, maybe this is 1, 2, and then I think I don't want to have so many repeats in the same column, because if I let's say I have 1, 1, 1, that forces me to never repeat in these two positions, or these two positions. So I'm going to do something like this. I can't repeat the 0, so I just put the zeros along the main diagonal and hope for the best. As I said, I don't want more than one repeat, so I'll put a 2 here, and then now that this is a 1, 2, this cannot be a 2, 1, this also has to be a 2, 2. I don't want another repeat there. I'll try a 1. This now has to repeat, otherwise this would fail. I don't want another 1 down here. And so finally down here I need to put this as a 1. And I see that this seems fine. Based on my very unsystematic way of filling it in, it kind of looks okay. But I realized that I can't go further, because if let's say this 1, 2, 1, 1, I can't put anything else here. I can't put zeros. And basically 1, 2 or 2, 1, I can only use one of them. 1, 1 or 2, 2, I can only use one of them. And I learned based on this kind of the key idea of the bound. The key idea for the bound is just that when you're working with, let's say, A, B, C, D, now assuming that there are no zeros in here, you can rewrite this using inverses as A to B and C to D. In other words, each of these pairs must be different mod P. And there are only two things that you could have, right? The ratio could only be 1 or 2 if it's not 0. And so this gives rise to an initial bound. I say initial because that's the first thing I came up with, and then I realized that after a while it does work. And I'm sure some of you had the same experience, right? You will get a bound. The bound is that n is at most p plus 1, because the p plus 1 comes from, there can be two zeros, let's say here, and then after that p minus 1 possible ratios. So that's the bound. Question is, can it work? Well, it would require 2 zeros in any pair of rows or columns, right? So without log, I can sort of just put on the main diagonal a bunch of zeros, and in fact, I'm going to try the p equals to 5 case to see if I can construct 6. That feels like the most reasonable way to come out with a good construction idea. Try the next case, which is definitely not so simple anymore. Now, it's actually pretty hard to look for any patterns, and I tried to just go with an experimental approach. It was quite bad. I also tried using a primitive root-based approach. Some of you who are familiar with primitive roots will realize that you could sort of change the determinant-like action of products into just a difference mod p minus 1. Didn't really help very much either. And so my motivation in order to construct is always, let me look for as many without logs as possible. The first without log is that I can swap rows and columns freely. That does not change the validity of selecting 2 rows and 2 columns and checking this value. Now this is like determinants. For determinants and specifically avoiding 0 determinants, when you swap rows and columns, it doesn't change the determinant. Another thing that does not change the determinant would be just scaling rows and columns. So if I were to, let's say, multiply the whole of the 10th column by, there's no 10th column here, the 5th column by 2. Now it will not change. If something was going to give me 0 mod 5, it would still be 0 mod 5 if I use that column where things got doubled, because doubling doesn't affect mod 5. Now because of this, without log, I can put the diagonal zeros like this, and I can scale the columns to all have a row and column of 1s like this. Now what follows is that I've got this other stuff. I need to make sure that no ratios repeat. In particular, no more repeats in these rows and columns. So it's going to be 0 to 4 in each row and column, which is basically Latin square. Latin square is like a Sudoku without the small boxes inside, right? This is a Latin square constraint. So I've got a Latin square, I said Latin square and I wrote Latin Sudoku. A Latin square constraint. There are actually lots of ways to have Latin squares. And then what I noticed is kind of like, okay, so imagine that I'm looking at the ratios. They're all supposed to be different, but this one can be anything. Now, the ratios are all supposed to be different, which means that the ratios I have got mod 5, I've already used 1. I've just got 2, 3, and 4 left as my ratios. And I realized that actually 2 times 3 times 4, this is actually Wilson's theorem. I can put a 1 there, which means that in order for the products to be the same, I need to cancel this out. Across diagonals, therefore, they must have this negative property. The property is that they must be negatives of each other, mod 5, which gives me this idea of, if I want the swapping row and column to give me negatives, that means that a possible way of labeling is just going to be x minus y mod n, then not mod n mod p, because that would be the most organic way to make the row column versus column row have negatives of each other. And so I tried this. It also does make the main diagonal 0, so that's consistent, which is nice. Essentially how that will look like is that this is, okay, since I wrote row minus column, this one technically will be minus 1. So this would be like 4 and 1, then 3, 2, 1. And then this is kind of just going to look like a cycle of your 1, 2, 3, 4s, or 4, 3, 2, 1s if you're looking at it row-wise. I notice immediately this kind of makes sense because of the fact that they have the same sum, 2 plus 2 and 1 plus 3, but a different two numbers. Now we know that in normal real numbers, if I've got two things with the same sum, the closer you bring them together and the further you bring them apart will change the product every time. I'm not sure whether it works mod P, so I can check and see. Alright, so what I have done here, I can just verify that if I have let's follow the question statement. AIK AJL minus AIL AJK. This is I minus K J minus L minus I minus L J minus K. And if you were to expand it, stuff cancel. This very nicely actually gives you I minus J K minus L, which of course in the P by P grid, so here a 5 by 5 grid, this is not going to be 0 since I only apply this to what is left over below. Right? And so therefore, of course, this is the construction that gives you n equals to P plus 1. It's a really nice question. This was a question that was proposed by Lim Jack, a very interesting question, and also it rewards a bit of understanding of, let's say, Wilson's theorem, determinants and such, without forcing you to have to know them to solve the question. The construction itself doesn't involve stating any of that, so that's pretty nice. And this takes us to the end of our SMO cycle for 2024. As usual, this is a bit belated, but feel free to leave any comments below, any discussion about the SMO. Hope you're happy with how you did. I will include the solutions in the description below, written out a bit more carefully. And as always, just remember that we're doing math because we enjoy it, so just after the competitions are over, continue doing math, but don't obsess with the results so much. Thanks for watching, bye for now, and see you again soon.